Swayam Prabha. Digital India. Educated India.
Now we will be discussing three-dimensional motion. We will discuss three-dimensional kinematics and then three-dimensional kinetics. We have studied quite a lot of dynamics. We have studied Newton's law, we have studied Euler's law. Then there is no reason to be afraid of the three-dimensional things, but generally students do not find comfortable in doing the problems related to three-dimensional kinematics or kinetics. The reason is that in three dimension, first of all, the first difficulty is that if you want to solve the problem with a piece of pen and paper, then three-dimensional objects have to be suitably represented there. So that the difficulty of visualizing. Sometimes you will see some figures in 3 dimension and you will not be able to visualize it properly. What are these things? The second is, as the number of dimensions increase, then the number of equations to be solved also increase, and also the corresponding terms in the equation. It is something like sometimes they increase not in the proportional way, but that by the order of n square or more. So obviously that there will be computational difficulties. Keeping those aside, the basic principle remains same. So there is no reason that if why we should not be able to understand the three-dimensional dynamics. Only thing is that we may not be able to solve the very lengthy problems here itself, but we will get this thing. And sometimes nowadays computational tools have become quite advanced, so therefore those problems can be solved by computers also. So therefore, we will discuss, but the objective of these lectures is just to understand the basic concepts, how to develop the equations, and understand some very interesting phenomena. Like in two-dimensional, you may be knowing that suppose a disk is rotating with a constant angular velocity, then there is no torque acting on this because there is no angular acceleration. But in three-dimensional, even if there is a constant angular velocity, there can be some torque. These type of things we will study here. So if I start from 3D kinematics, so in this we first study the motion of rigid bodies in three-dimensional space. Now we start the lecture by discussing different type of motions again, which we have already discussed in the previous this one, but mostly we give examples from 2D space. Now we will give examples from 3D. So there are basically different type of motions. One is translation. In translation, there are two type of translations. One is the rectilinear translation, we say, in which the translation between any two in this translation, any 2 points in the body will move along parallel straight lines. So, you know that, and suppose there is a line in the body, that line remains parallel to itself. So, naturally in the translation angular velocity is 0. So, but rectilinear translation, that the 2 points move along parallel straight lines, that is the point, they have to move in a straight line, then it is rectilinear translation. Then other type of motion is curvilinear translation. In curvilinear translation, 2 points in the body will move along congruent curves. So, there will be 2 type of this one curve. So, you know that this is one type of that curve, and then another type of this one. So, what happens that in this there, say suppose this is a point, it is moving, and similarly parallel type of curve is there on which also it is moving. Now, in either case every line in the body remains parallel to its original position. In either case, that means in both in rectilinear and curvilinear translation, every line in the body remains parallel to its original position. So, that is the point. Now, we see that in this animation, I am going to show you one animation. The cube will undergo translation along a curve. This is not a planar curve, this may be a space curve. That means it is not, one plane is not there which can encompass this curve. A line on the face of the cube will always remain parallel to itself. So, for example, I am playing this animation, just see this line, although this cube is moving in a curved path, but this line always remains parallel. So, this is an example of a translation. Okay, that sometimes that if you sit on a merry-go-round, that vertical type of this one, in that you see that you actually move in a circular path, but still you remain means you your body remains basically in the same position. That means a line in the body will remain parallel to itself. So, therefore, what happens that in translation, a line on the face of the cube always remains parallel to itself, that this animation shows. Now, if you consider, see this figure, consider 2 points A and B on the body, that body has been shown. Now, if RA is the position vector of A, this point A has been shown here, RB is the position vector of B, and RA/B is the position vector of A with respect to B, then VA is equal to VB, because what happens that you can always see, because RA is equal to RB plus RA/B, sum of these vectors, and RAB is always constant because the RAB is not rotating. So, therefore, if you take the derivative, you can always say that R dot A will be equal to R dot B, that means VA is equal to VB. So, therefore, any 2 points on the body will have same velocity because R dot AB will be 0, and similarly we can say, if we take the derivative of this, so we can say A is equal to AB. So, therefore, acceleration of 2 particles will be same. So, that is the specialty of translation. This is because the magnitude of RA/B remains constant with time, because the body is rigid. In the case if the body would have been flexible, then this relation was not correct, because there may be R dot AB in the flexible body, different even in translation different points may have different velocity, but we are studying the rigid body mechanics. In rigid body, you know, 2 points are having same velocity, same acceleration, and so therefore, that is the specialty of this one. Thus, in the translation of a rigid body, every point in the body has same velocity and acceleration. Thus, the velocity and acceleration of the whole rigid body can be specified by specifying the velocity and acceleration of one point. So usually we specify the velocity of the mass center. That means if we say that mass center is moving with velocity, then the whole body is moving, all points in the body are moving with the same velocity. So and acceleration also, that is the mass center. Now we have that, so let us discuss another type of motion. This was the translation, and the other type is fixed axis rotation. Now a rigid body is rotating about a fixed axis O dash in space. Suppose this is O dash is a fixed axis that is rotating. The angular velocity omega is represented by a vector along the axis. So it is rotating about that axis. So our convention is that about the axis about which the body is rotating, that axis will be called, that axis will represent the vector of the angular velocity. Angular velocity vector is having the direction of that vector, and magnitude is of course the magnitude of omega. So this is the thing. You see that from here you are observing that this is a body, XYZ system has been shown, and this is a theta, and this is a perpendicular, this is any arbitrary point P which is at distance r from this one, and this distance is d. So this is the type of this thing, and after that we go to this next. So if you view this one like this from this one, and you see by viewing from this side from top, you see that it is rotating counterclockwise. If it is rotating counterclockwise, then your velocity, angular velocity vector will be directed towards you. If you observe that somebody is rotating and from the top you see, and the direction of rotation is counterclockwise, then the angular velocity vector will be towards you. And if the body was rotating clockwise, then the angular velocity vector will be away from you. So that is in the opposite direction. So therefore, if you view as shown above and observe that the body is rotating counterclockwise, then the vector omega will be directed towards you. If the rotation is clockwise, the vectors will be directed away from you. The magnitude of omega is equal to the angular speed omega of the rotation, that is the tangential speed of a point divided by its distance from the axis of rotation. Magnitude will be like this, that if you find out that point P is there, point P has got some tangential linear velocity. So what one has to do, you divide it by this small d, that becomes the angular velocity, that is the magnitude. Now let us go to that this point. Let P be any point on the body. You now concentrate on this figure, and d its distance from the axis. D is the distance from the axis. Then P has the speed omega times d. Okay, this is, and let R be the position vector of P. Refer to coordinate system which you have chosen with origin O on the axis of rotation. Then you can see very well that if this is theta, then d is equal to basically magnitude of R times sin theta, where theta is the angle between omega and R. Omega is the velocity, angular velocity vector, and R is the position vector. Therefore, in this case, omega dot d will be omega times R sin theta, and which is equal to omega cross R. So this is will be omega cross R, because omega d, that can be written as omega, magnitude of omega, R sin theta, and you know that it is same as the magnitude of omega cross R, because cross product of two vectors omega and R is omega R sin theta. Omega d is the tangential speed. There is no normal component of speed, because it is rotating, this point is moving in a circular fashion. So therefore, this is the, thus the velocity of point P is basically V is equal to omega cross r. So you have got now a formula that velocity is equal to omega cross r, that is. So note that the velocity of point P is normal to both omega and r. That means the tangential velocity will be normal to omega as well as position vector. The acceleration can be found by differentiating this above equation. That means differentiate V is equal to omega cross r, you can get the acceleration. So you differentiate A is equal to, if you differentiate, that is omega dot r, omega dot cross r plus omega. Now if you differentiate r, so r is rotating actually this one, so this is r dot, so r dot will be basically again omega cross r, since r dot is equal to basically V, that is omega cross r, because that we have seen r dot is equal to omega cross r, that is V. So therefore acceleration comes out to be omega dot r plus omega cross omega r. Now since the direction of omega is fixed, suppose because motion is we are discussing the case in which the axis of rotation is fixed, that is along the axis, and only magnitude can change. It has the same direction as omega. So therefore what happens, that if you see omega dot has same magnitude as omega, so omega dot is also along that one, and omega dot is therefore omega dot r has the same direction as omega cross r is equal to V. Thus in the equation the first component, that is omega dot r, which can be written as alpha times r is equal to V, is the tangential component of the acceleration. So that is the tangential component of the acceleration. And if we indicate omega dot by alpha, then the angular acceleration, then tangential component may be written as alpha times d. So that is the thing. So omega dot is equal to alpha and alpha cross r. So its magnitude will be alpha r sin theta, that means alpha times d. That is the tangential component of the particle is of the particle's angular acceleration of the particle is the angular acceleration times the perpendicular distance from the axis. That is the thing. So you get. Now let us look at the other component, that is omega cross r. This component is in the plane of rotation, that is normal to fixed axis and perpendicular to tangential direction. Therefore it is basically in the plane but in the normal direction. It can be easily seen that the magnitude of omega cross r is omega square d, because magnitude of omega is omega times d and omega is there, so omega square d. So this is that component, centripetal component of this one. Now since V and A are perpendicular to omega and omega dot, therefore V dot omega is equal to 0. Why? Because V is always tangential velocity is always perpendicular to the direction of omega, that so V dot omega is equal to 0. Similarly V dot omega dot is also 0. Dot product of velocity and angular acceleration, tangential velocity and angular acceleration is 0. Similarly the acceleration into omega, that is also equal to 0, and then acceleration into omega dot, that is also 0. So this is these are the equations. So these are important things. Now we having discussed the rotation about a fixed axis, that means axis of rotation is fixed. Now we can discuss the case in which the rotation is about a fixed point. Point is fixed but axis may not be fixed, axis may be changing, okay, like in the rotation of a top axis is there, so that axis keeps changing. So now we will study the situation in which axis of rotation is not fixed, however it passes through a fixed point. Note that finite, one point interesting point I will bring here, that finite rotations are not vector. Suppose you know that there are rotations, axis is rotating, so we are going to discuss the rotations. So one point I would like to emphasize, that that like we say displacements can be added like a vector. Can we add finite rotations in 3 dimension like a vector? No. To demonstrate it, we have shown some animation. We present animation. Now here in the I show animation in which you rotate the block by 90 degree about z axis first, and then 90 degree about y axis, and see what is the orientation of the block. So it is because, so like this. Now if I say that this is a block, this block cube, different faces have been shown by different colors. A is top green type, 2 is slightly brown, is 3 is blue. Now here if I show z axis rotation, rotate this by 90 degree about z axis. Now this face has come like this, and if I say y axis, then you have got this type of orientation. Can see it again, z axis rotation 90 degree, then y axis rotation like that. Now in the next figure, rotate the block by 90 degree about y axis first, and then 90 degree about z axis. See the orientation. You will find that both orientations are not same. Suppose I have rotated it y axis, you got like this, and z axis I am rotating, I got like this. So I got totally different type of things. See this animation again, rotation by 90 degree about z axis, rotation by 90 degree. You can do these type of experiments with your for learning and more clarity by taking some book and rotating it, that 90 degree, and then again 90 degree about some another axis like that, and you see that finite rotations are not commutative. Okay, it depends like in which order you have. So this simple example illustrates that finite rotations are not commutative and hence cannot be treated as vector, and this is the thing, they cannot be treated as vectors. So this is the thing. On the other hand, infinitesimal rotations may be treated as vectors. For that we illustrate something. Now we will see that in the animation it is like this. Suppose you press OK, first 1A. So I am rotating it first here, then that about different axis like that, and in this I am changing the axis, I am rotating it like this, and then here I am rotating it about z axis here. So that here it has basically the rotations have produced the same result. We can see it again. First rotate it about z axis, then rotate about y axis. Here first rotate about y axis, then about z axis. We got the same thing. See again, these are small rotations, this is like this, and then after that you get like this, and after that reset. So therefore, thus if d theta 1 and d theta 2 are small rotations about 2 axes, then d theta is equal to d theta 1 plus d theta 2. If you divide this by dt, then we can say that omega is equal to omega 1 plus omega 2. I can divide it by t, dt limit, dt tends to 0. So therefore what happens that in this case, so velocities can be added like vector. For example, now consider the following arrangement. like this, in which there is a disc which is rotating at omega 1 and there are two bearings on which this shaft is mounted, and there is a disc that is also spinning about another axis. So, if I show that x, y, z axis, so one rotation of the whole disc is about z and this is spinning about y axis. So, in this case what happens that in the disc A is rotating about the vertical axis with an angular velocity omega 1. Disc B is mounted on a shaft supported by two bearings on disc A. The angular velocity of omega is omega 1 plus omega 2. Therefore, the combined velocity omega is equal to omega 1 plus omega 2 vector. So, therefore, combined velocity vectorially is like this. So, angular acceleration when the magnitude of omega remains constant but the direction changes. So, we can find out the angular acceleration in that case. The angular acceleration alpha is the time derivative of angular acceleration, that is A is equal to omega dot. That is, we can write this big omega cross this omega small, where this big omega is the precession angular velocity of omega. So, that is the expression for angular acceleration if the axis is also precessing, that is called precession motion. Like example, in this you see that there is a disc which is rotating, on this is mounted some shaft and on which there is a rotor which itself is spinning with omega 2. But the axis of rotation of omega 1 is fixed. However, the axis of rotation of omega 2 is changing, then the magnitude of angular acceleration of B is omega 1 into omega 2. So, that is the thing we have got, and discussed about translation, then about rotation about a fixed axis, then we discussed rotation about a point. Now, we discussed naturally the general 3D motion. We now discuss general 3D motion. Now, consider a rigid body which has an angular velocity omega. So, I show first the axis system in 3 dimension. You have this is y, z, x, o. Now, this is a body I am showing. Now, I can, this body is having angular velocity omega. I can show the angular velocity vector omega. It is in this direction. At the same time, the body may be translating also. So, if I choose an axis system x, y, z on the body, this is y, then z, this is x, and where small o is the origin, a point on the body. If we choose another axis system, that is oxy, this is like that, which is considered to be fixed, that is the velocity and acceleration of point O is always 0, and we assume that xyz axis remains parallel to xyz. So, that means we have attached a axis system which remains parallel to xyz. Then the velocity of a point P, this point, suppose there is a point P, with respect to O may be written as Vp is equal to velocity of point P, Vp is equal to V0 plus omega cross R P O, small o, this is small o. So, that is the thing, that you get Vp is equal to Vo plus omega cross this one, and similarly the acceleration of this one AP can be written as AO small o plus omega cross R PO plus omega cross R P O. Now, so these are the expressions which we developed while studying the kinematics also. Now I will take that one example. Suppose consider this ring. Suppose there is a shaft. No, this is, and these are the bearings. Here also these are bearings. Suppose this is just supported that axis, and then in this you have attached one ring like this, and here by pin joint another ring is there. And if it is rotating with omega 1, and let us say this axis is x, y, z. This axis, if I attach another axis system, if this point I call A and this ring is B, the third ring is BC. Here I attach small x, then you have y, and then this is z. This is omega 2. Now y axis which I have shown is perpendicular to the plane of your screen. Now x, y, z and capital X, Y, Z both are parallel. In that case, we can always write that VC is equal to VB plus omega 2 cross RC cross B. Now what we do that about? So this is the expression, and now VB is equal to basically omega 1 times L, because it is rotating by omega 1, times J plus omega 2 cos J minus L cos theta I plus L sin theta K. Which if you do that, then simplify that, you get W1LJ plus W2L cos theta times K plus W2L sin theta times I. So that type of expression you get. I could have taken the another reference system also, that is rotating reference axis. Now if we take x, y, z, o, this is a fixed axis system, and if we take a body like this in 3D, but if we take a small o origin, and this is x, y and z. Now this axis system is also attached, but this time it is not parallel, instead it is rotating also. So therefore what happens, that in this suppose x, y, z rotates with angular velocity omega, that means rotation of axis is by big omega, which is different from the angular velocity small omega of the body. So omega and omega in general can be different, but then you can easily prove that if I take I axis about this and j about this other y, then you can easily prove one point that I dot unit vector dot is equal to basically big omega cross I, angular velocity of the axis system cross product with I. Similarly, you can say j is equal to j dot equal to j. Similarly, k dot is equal to omega cross k. Here dot indicates the time derivative. Now the expression for the velocity and acceleration of point P then become Vp is equal to, suppose we have a point P on the body, so that becomes Vp, then Vo small plus omega cross Rpo plus Vrel, relative velocity of that point, and Ap becomes equal to Ao plus omega dot cross Rpo plus omega cross Rpo plus 2 omega cross Vrel plus Arel. These expressions we have already discussed, but we are just only re-looking at them from the point of view 3D kinematics. Now in this case, Vrel is basically in 3D, it is x dot I plus y dot j plus z dot k, and Arel is x double dot I plus y double dot j plus z double dot k. Now if the axes are rigidly attached to the body, then obviously omega will be equal to omega, and in that case, since they are rigidly attached, therefore Vrel and Arel both will be 0, and in this case the equation reduces to your previous equation, that is omega cross this one Rpo. So this is what that type of thing happens, and now we see that we now solve this that same problem which we just solved this thing, that we will go back to that previous slide, and here we have solved this problem. Now this time we attach the axis system to link 1 itself, that means it rotates with the link 1, then in that case we will be getting Vc is equal to Vb plus omega 1 I cross minus L cos theta I plus L sin theta k plus omega 2 j minus omega 1 I L cos minus L cos theta I plus L sin theta k, and if we simplify, then this becomes basically omega 1 L j plus omega 2 j cos minus L cos theta I plus L sin theta k. So we get the same equations as we got before, same velocity. So therefore one can take different type of axis system and he can get the different same result. Now we give that another example, and now if we go to that one, then it is like this. This is, suppose we do this thing, a link is, suppose there is a shaft here which is put in some bearing and it is rotating with omega, and you have axis attached here z, and this is x, and this is VA. Then the relative velocity of this is VA is equal to omega cross R A O plus VL, that is omega cross R times J, this is y direction, J plus VL, and this one absolute acceleration will be omega square R J plus twice omega VL I, where 2 omega VL is the Coriolis acceleration, and that is what that it happens. So these equations which we discussed, that can be used for three-dimensional things also. Now we discuss about that, just pay attention that how many independent coordinates a body has, rigid body. Now rigid body is composed of so many particles. Supposing a rigid body has got n particles, if there are n particles, no rigid body is composed of, right? Although we will say that rigid body n tends to infinity, otherwise it will not be continuum. We cannot have discrete set of particles. Now suppose there are n particles, then 3n degrees, each particle has 3 degrees of freedom, x, y, z. So total degrees of freedom are how much? 3n, since each particle has 3 degrees of freedom. So therefore 3n coordinates are needed to specify the body. However, these coordinates are not independent, they are related. Why? Because in the rigid body, distance between two particles is fixed. So one particle is connected to other n minus 1 particles. Thus we write n minus 1 equations relating the coordinates and distance. Similarly, for the second particle we can write n minus 2 equations, since the equation relating this and the first particle has already been written. Similarly, for third particle we can write n minus 3 equation. Thus total available equations are n minus 1 plus n minus 2 plus 1, and this is equal to, if you do that, it will be n minus 1 n minus plus 1 by 2, that is half n minus 1. Now for large n, obviously these equations, that total available equations, these are constraint equations, they are more than, you know, that 3n, because for suppose you take n is equal to 100, so 3n is 300, but this will be 100 times 99 by 2, that means 50 into 99, 50 into 99, so almost you know that 99 into 50, so that is 45 and 49, so 4950, where you have, so these are much more than this thing. So what is this thing? So but all of these equations are not independent. So therefore this way we cannot ascertain. There will be, why? Because now, so the another way to understand that, if we know the coordinates of 3 points, let us say there is a rigid body and you know the coordinates of 3 points, this is the thing, 3 points coordinate is known. Then for any point, if you take any 4th point in the body, there are, like if I take this point, then there are 3 equations relating coordinates with the distance of the points. So therefore this is like this, this is like this. So this is the thing. So therefore once you have fixed up 3 points on the body, then all points get constrained. They cannot have their independent, you know, that degrees of freedom. So we can only take 3 reference point, but the 3 reference point themselves are also not independent. There are 3 equations of distance actually. Thus the independent degrees of freedom are 3 into 3, 9 minus 3, that means 6. So there are only 6 independent degrees of freedom. Now therefore that since there are 6 degrees of freedom, now if we fix a point O on the body and some coordinate system, then 3 coordinates are needed to specify the origin of the coordinate system. Since total 6 degrees of freedom are required to specify the body, 3 coordinates are needed to specify the orientation of the axis. So therefore there are many ways of specifying the orientation of a Cartesian set of axis relative to another set with common origin, but most common is the Euler angles. So most common is Euler angles. Now we will explain this by animations. Euler angles are defined as 3 successive angles of rotation. Many conventions are followed, but the sequence implied here is started by rotating the initial system of axis x, y, z, suppose you have, by an angle alpha about x axis. The resulted coordinate system is labeled as the x2, y2 and z2. So you know, now this is the z2 axis is the same as z1 axis. So therefore suppose you have a system that it is x1, y1 and z1, now you rotate and this axis is same as that one. So you give the first rotation, you got another system x2, y2, z2. It has rotated about the z1 axis by an angle alpha, but the z2 is same as z1 in that direction. See this animation again. Initially x1, y1, z1, now rotate it. So first rotation has given x1, y1, x2, y2, z2, right? This is the thing. So now then we go to the next, we give the second rotation now. Now in the second stage, the intermediate axis x2, y2, z2 is rotated about y2, about this y2, to produce intermediate set x3, y3, z3. So now it is rotated about this y2. So this is how it will rotate. Now let us see the second rotation. So by second rotation, y3 is same as y2 in the same direction, but these has rotated x3 and z3. and those angles are beta. So that rotation is beta. Now the intersection of x2y2 and x3y3, this is x2y3 and x3y3, is called line of the intersection of x2y2 and x3y3 planes is known as the line of nodes. So these two planes intersects, so that is called line of nodes. This is the thing. We will see it again. This was x2y2 plane, and then this gets rotated. Now this is x3y3 plane, so their intersection will be called line of nodes. Now we see finally x3y3 z3 is rotated about z3 by an angle gamma. So therefore what happens, we will reset that and see third rotation about z3, so gamma. So we get another type of this thing. So like that we do and we understand that thing. But this is not the only way. Parallel angles are not the only way to specify the motion of this thing. There are other, this one, and once we have the rotations, these rotations can be represented by the matrices, and finally we can multiply the matrices and to get the final outcome. Now we can have another type of rotation that is called more common convention in engineering application is like this. Now that is, we can have the axis system and we can have yaw. This is called yaw motion. That means about this vertical axis the plane is moving, that is yaw motion. Then we have got pitch motion. It is moving pitch motion. Yaw motion is, see, we said yaw about this one, and pitch about this upward, that that pitching motion about this axis transverse. This is this axis is called this one pitch, and roll is about that longitudinal axis. This is roll motion. So this is thing. So these type of that conventions can be done. Now, so therefore we see that now these are the motions, and now we will be discussing, till now we have discussed kinematics, now we have to discuss kinetics also. So before that, let me just give that. So in 3D, so really you got some appreciation that what all means, why visualizing of that 3D kinematics etc. You have to understand the type of angular system and all these things. Now in the case of parallel angle, here suppose you have got D is equal to cos alpha sin alpha 0 minus sin alpha cos alpha 0 0 0 1, and then the rotation about another axis can be specified by cos beta 0 minus sin beta 0 1 0 sin beta 0 cos beta, and the rotation about the third one B is cos gamma sin gamma 0 minus sin gamma cos gamma 0 0 0 1, and if we denote the old axis system by x y z and new by x prime y prime z, then you have these equations: x prime y prime z prime is equal to BCD x y z. So this is the thing. So you have to say like this. So like that we can find out the relations. So we get the coordinate systems relating one axis system with the other axis system. So this way it can be done. Now also, so once we understand these things, so we can have, so for any particular that body, we can have three coordinates x, y, z of the origin, and we can also have alpha, beta, gamma. These are the angles. With this we can describe this thing. Now in the next lecture we will be discussing the Euler's equations. That means we will start dynamics, and then we will also study one phenomena of that gyroscope, the gyroscopic motion also we will study. That will be the topic of the next lecture.